Okay, thanks for the introduction, and also thanks Stefano for giving a very nice setup for my talk. So I'm going to focus on one of the problems that was mentioned in the previous talks, and this is basically will be a much, would say, more focused talk than the previous one. And I'm going to start with some introduction. It was essentially covered in the previous talk, but I have slightly maybe different emphasis and notation. So I will go over like the basics very quickly. So a classical problem in cryptography is the following. So we have an adversary that tries to distinguish a random permutation from a random function. Okay, and these permutation functions are defined on the set of size n. Okay, and the adversary has like a budget of q queries. Okay, so that's a very classical problem, and it's well known that the adversary has an advantage that is bounded roughly by q squared, the number of queries squared, divided by n. Okay, and distinguishing between these worlds. Okay, and this is how it's written more formally, but yeah, I'm not going to be very formal in the remainder of this talk. So this bound is also called the switching lemma because it allows you kind of to switch from a random permutation to a random function up to the birthday bound of q equals square root n. Okay, and this is kind of widely used to establish security proofs of crypto systems up to the birthday bound. For example, Stefano mentioned a few modes of operation. Okay, so this is kind of classical and very useful. So it depends on the setting, on the actual setting, and Stefano actually showed an example in the beginning where this is useful, like in modes of operation, where you switch, you do some switch between a permutation and a function, and then you can kind of think of everything as being random, and then the security proof follows. Okay, also you usually need some computational assumption there, like, but this is essentially information theoretic, and once you combine it with computational assumptions, then you get the security proofs. Okay, so in this proof, and this bound, which bounds the advantage of the adversary, it is tight. Okay, and it's not very difficult to see. Basically, the matching algorithm to achieve this bound is the following. So you issue q queries to the random function or the random permutation. You store them in memory, and you just look for a collision, which means you have two different inputs. F applied to two different inputs gives you the same output. And this is basically allows you to detect in which world you're living in. And if you do the analysis, basically this is the advantage that you get. So this is tight. Okay, however, the algorithm requires you to store all the answers to the query, so it requires memory of roughly q bits if we ignore logarithmic factors. Right, so now the answer is what if we're considering memory-restricted adversaries, which have less than this amount of memory. Okay, so in general, what you can do actually is you can achieve the optimal bound of q squared divided by n using some cycle detection algorithms. And again, this was mentioned in the previous talk, which actually require a very small amount of memory, logarithmic amount of memory. So in this sense, this question, if you allow these cycle detection algorithms in settings in which they are applicable, then this basically essentially solves the problem because you can do it with, you can distinguish with negligible memory. However, in some settings, these cycle detection algorithms are not applicable. In particular, these cycle detection algorithms require adaptive queries to the primitive, but in some settings, such as attacking modes of operation, it's not possible. I mean, it depends on the power of the adversary. It's just not possible to apply them. Like a different, maybe a slightly more restricted setting, ask what if the adversary has a memory restricted to, say, S bits, but is only given access to a stream of, say, Q elements that are produced either by a random function or a random permutation. And now he wants to distinguish which is the case. Okay, so this is the basic problem that I'm going to focus on. And this problem was actually first considered by Joseph and Stefano at Eurocrypt 2019. Okay, so the setting is that, again, you have a stream of Q elements. You don't know if they are produced by a random function or a random permutation. Okay, but, and you have a memory of S bits. Okay, and you want to kind of distinguish between these worlds. Okay, that's the setting. So I think this is kind of a very basic and natural problem, and I find it a bit surprising that it was only came up in 2019. And yeah, so what basically Joseph and Stefano proved is that an adversary with S bits of memory and access to a stream of Q elements drawn from either a random permutation or a random function have a distinguishing advantage, which is bounded by Q, the number of quays, times S, which is the memory, divided by N, which is basically the set, the relevant set, the domain for the function and the permutation. Yes?
The elements are chosen at random?
Yeah, so it depends. If you're in the random permutation, they are just chosen at random, but without replacement. And if they are chosen from a function, they are chosen uniformly at random, independently. So this is the setting, okay? That's the setting. That's a very basic setting that we have. Okay, so this is kind of the streaming switching lemma that was proved at Eurocrypt 2019. And also what they showed is that this has applications for obtaining some security proofs against memory-restricted adversaries for some modes of operation. Okay, so you can go beyond the standard birthday bound if the adversary has a restricted amount of memory. Okay, so this bound allows you to obtain these proofs. Okay, so this seems kind of useful. However, there were a few limitations to this bound. The first is that the proof is actually based on some unproven combinatorial conjecture, which seems natural, but again, the proof is not in a way complete. And the second is that you have this square root term here, which seems to be not tight. I mean, it kind of seems that the right bound should be without this square root term. When Q, it's relevant when Q times S is much smaller than N. And to see this, let's assume that S is equal to Q. So essentially, you can store all the outputs. Okay, you have sufficient memory to store all the outputs. And then essentially the standard switching lemma that I showed you at the beginning applies. Okay, so the standard switching lemma gives you a bound of about Q squared divided by N. But if you plug in S divided by S equals to Q here, you get the square root of this, which is worse when which is a weaker bound when Q times S is smaller than N. Okay, so two things. Like I said, the proof is based on some conjecture, and the second thing, it seems to be not tight for a certain regime of parameters, kind of natural. Okay, so these are the limitations. So what basically I do in this work is overcome these limitations. Okay, so in particular, I'm going to prove a new so-called streaming switching lemma, which essentially gives you the optimal bound, Q times S divided by N, up to a logarithmic factor in Q. Okay, so this is what this new work is about. And this proof is tight up to logarithmic factors. And in order to see that it is tight, let's consider the following algorithm, or upper bound if you want. What does the trivial algorithm do in order to distinguish between the roads? So you, again, obtain a stream of Q elements. You want to know whether the stream has repetitions or not. So what is the trivial thing to do? You just store the first S elements of the stream, and then trying to find the collision between these elements to the stream. Okay, and it's not difficult to show based on standard birthday arguments that the advantage that you get is roughly Q times S divided by N. This is a generalized form of the birthday bound because essentially you have S times Q pairs here. So this is kind of the advantage that you have for the algorithm or the attack if you want. And this matches, again, up to logarithmic factors, the streaming switching lemma. Okay, so this is essentially tight. Another thing that you can see is that when S is equal to Q, then what we get here is basically Q squared divided by N, which is the original switching lemma. So in a sense, this lemma is kind of an extension of the standard switching lemma to the streaming model. So it's kind of a direct, direct continuation of it, if you would like. Okay, so now I'm going to go into the proof, right? How do I prove this new streaming switching lemma? And the main idea is basically to use communication complexity in order to prove this bound in the streaming model. Okay, so I'm going to reduce from a communication complexity problem with strong lower bounds on the required communication to the streaming. So before I go into the specific reduction, I'm going to just state the general framework of how these reductions are done. This is something that's been used for many, many years. So here is a general reduction framework from one-way communication complexity to streaming. Okay, so Alice and Bob basically want to solve some communication complexity problem given access to a streaming algorithm. Okay, so how does it work? So Alice and Bob receive some inputs, okay, and they review their concatenated inputs as a stream. Okay, and again, they are given access to the streaming algorithm. So what Alice can do is just simulate the streaming algorithm on her input. Just feed it her input. And then she's going to pass the state of the streaming algorithm to Bob, which continues the simulation on his input and output the result. Okay, so this is a very classical way to reduce from communication complexity to streaming. Okay, and what this shows you, that basically the following thing, that the streaming algorithm with memory S gives a one-way communication complexity with communication cost of S, right? Because Alice, all it has to do is just to transfer the state of the streaming algorithm to Bob. And the state is bounded by S bits. Okay, so, but here we're actually in the standard ways to use this is actually to obtain lower bounds, to show the bounds on the streaming algorithm. So we're going to apply the contrapositive. We're going to say that a lower bound on the cost of the communication protocol. So if the communication protocol is is difficult in a way, okay, so you obtain a lower bound on the memory of the streaming algorithm. Okay, so that's the same argument, just flipped around. And this is basically, like I said, this is very standard and completely independent of has been done for many years. Okay, so now let's try to apply this general framework to the concrete problem that we're dealing with, just distinguishing between a stream chosen from a random permutation and a stream chosen from a random function. Okay, I'm going to try to apply this framework, and here's a first attempt. Okay, so here's the attempt. Each player gets half of the elements, like Q divided by 2 elements. And like these elements are chosen either from a random permutation or a random function. So basically, this is the setting. Okay, so do you think it's good? Will it help us like to achieve any meaningful bounds? Okay, so the answer is no, just simply because the streaming problem is not, the communication complexity problem is not difficult, right? It's trivial. In order to see this, for example, if Q is larger than the square root of n, then if these elements are chosen for a random function, then Alice with good probability has a collision within the elements she obtained, so she can trivially output the result without any communication. So the communication complexity problem is trivial, so it will not give you anything meaningful. So we need to reduce it from a hard communication problem in order to get something meaningful, and this simply does not work. Okay, so I mean, the thing to notice here, again, this is very basic, is that here in the communication complexity setting, each player has unlimited resources. So Alice has unlimited resources. We're just counting the amount of communication between Alice and Bob, and she can trivially just, if she has a collision, she can trivially detect it. Okay, so in a way, this kind of, if you kind of look at the general setting, we have a general restriction on what we, on this reduction. In order to obtain a hard communication complexity problem, kind of the local views or the marginal distribution for Alice and Bob should be the same for both distributions that we're trying to distinguish. Otherwise, each one can just trivially locally output the answer. They don't need to communicate. So both need to have kind of the same local views. Okay, and actually this is, if you think about this restriction, it's impossible to comply with when we're considering like the random permutation and random function distributions. There's no way to distribute the stream in such a way that this restriction would hold. Okay, so this just doesn't apply. So we need some way to get around this. It seems that this approach is doomed to fail. However, we can use additional tricks, and one additional trick that we can use is we can try to apply hybrid argument. What do I mean by hybrid argument? Well, we'll define some intermediate hybrid distributions between a random permutation and a random function, and we're going to actually prove the indistinguishability of neighboring hybrid distribution by a reduction from communication complexity. Okay, so this again, nothing. I'm not saying anything new here. This is kind of a general approach that has been applied before. Okay, so in standard hybrid argument, what I think for our specific problem would actually define Q hybrid games. So how would game I be defined? Again, we're trying to get from a random permutation to a random function. So we would define the game I as follows. So the first Q minus I elements are chosen without replacement, meaning that they're chosen from a random permutation. And the remainder, like the suffix, would be chosen with replacement from a random function, like completely independent of the remainder. Okay, that's one distribution. And the neighboring distribution would just sample the first Q minus I minus 1 prefix without replacement, meaning from a random permutation, and the rest would be sampled from a random function. Okay, so this is a completely valid approach, and you can actually kind of do the math and see what you gain from this. But if you kind of write out the equations in a standard way, then you apply the hybrid argument, and the boundary you get is far from being tight. And basically, I'm not going to get into details. The reason is that there are too many hybrids. Okay, when you sum up the advantages, it just blows up, and you don't get a tight bound. at least if you do it in the standard way. So basically, this does not give you the tight bound. Okay, so we need to something else. So let's again go back and formulate our goals. So what are our goals here? We want to construct hybrid distributions such that the following two restrictions apply. The first restriction, like I said before, so Alice and Bob, it should have the same marginals, like the same local view for neighboring hybrid distributions. That's the first restriction. And the second is the number of hybrids to be small. Okay, and what does it mean? So we're trying to, again, to start from a random permutation. We want to get to a random function. So essentially, it means that each hybrid needs to break many dependencies among the elements. Right, because again, random permutations, you have no collisions, the elements are dependent. Random function, the elements are completely uniform. So you kind of want the hybrid to break a lot of dependencies between the elements. Okay, again, this is kind of natural, and these requirements seem somewhat conflicting because on one hand you want to preserve the marginals, on the other hand you want to break many dependencies. Okay, so there is like tension between these two requirements. However, as I will sketch in the next few minutes, if I have time, how much time, by the way? Okay, so if I have time, hopefully I will have time. Okay. Okay. Okay, so I'll take the 3 or 5 seconds, and as we will see, well, in the sketch, these requirements can be actually, these cause some loss. This results in some loss, but the loss is not that big. The loss is logarithmic. Okay, in the bound. Okay, so let's see. Let's start. Okay, so let's start by defining the first hybrid game. Okay, again, we want to get from a random permutation to a random function. So let's denote the sequence. I can denote it as I wish. So the first half of the stream I'm going to denote by x's, and the second half by y's. Okay, and of course the first distribution it is fixed. Like all the elements are chosen from permutation. So all these elements they're distinct. And the neighboring distribution is going to be defined as follows. Okay, so in the neighboring distribution, these two halves are going to be chosen from independent permutations. So you cannot have collisions within each half, but you can have collisions in each half. You cannot, but you can have collisions like x1 could be equal to y2, for example, because these are two independent permutations. Okay, so this is the first hybrid that I'm defining. And what is the matching communication complexity problem that we are reducing it from? So it is kind of, this is kind of trivial. Alice gets the first half of the sequence, Bob gets the second half, and they just want to decide whether they obtain elements chosen from the same permutations or from independent permutations. Okay, that's the communication complexity problem. And you can see now that the marginals are identical because each one in both cases gets just q divided by 2 elements chosen at random from some permutation. Okay, but they want to, of course, in the first case, when it is chosen from the same permutations, then there is correlation. Otherwise, there is no correlation. Okay, so the margins are identical, but the hybrid kind of breaks the dependency among the two halves because of the second distribution. Okay, so this is basically the communication complexity problem, and this is an ad hoc problem that I'm going to call permutation dependence, whether the permutations are the same or they are independent, okay, or PDEP in short. Okay, so Alice and Bob simply want to decide whether their inputs were drawn from the same permutations or from independent permutations. Okay, and now the reduction from streaming is the trivial reduction that I showed you before, like the standard reduction. There's nothing special going on here with the reduction to streaming from a permutation dependence. Just the classical one. However, the question is this permutation dependence problem really hard? I mean, do Alice and Bob need to communicate many bits in order to solve it? Okay, and what I show, I'm not going to show you the reduction, but what I show is that it is hard because you can reduce it from a classical problem in communication complexity, like the most classical one, which is called set disjointness. And actually, I'm going to use a variant here, which is called unique disjointness. I'm not going to get into the details. But basically, in this disjointness setting, it is a worst case problem. Alice and Bob get two sets, and they want to decide whether the sets are intersect or they are disjoint. Okay, that's the communication complexity problem. And like I said, it is a worst case problem. It is not a distributional problem. And I'm going to, well, I'm going to use a theorem that is actually proved only 6 years ago. And in a way, it's a bit interesting because this is like a very classical problem by Braverman and Moitra. So the theorem says that if an Alice and Bob communicate C bits for disjointness, in the worst case, that their maximal advantage is bounded by C divided by N. So when C is about N, this was known from the 90s by Razborov, 92, I think. Then this was known. Like if you want a constant advantage, and you need to communicate essentially, in the worst case, all the input. Like Alice has to communicate all the input. But actually, this bound for when C is smaller than N was only proved 6 years ago, which is a bit surprising, yeah.
But they proved it for the general communication complexity setting, right? You are in the one-way communication setting.
No, this applies in the also in the. No. In the first hybrid. In the next, there will be some complications. I'm not sure I will get into them, but this is just for the first. Okay. I will actually, I'm not going to have time to get into it, but in the next hybrid, the reduction becomes more complicated and I actually have to go back and forth. Okay, so I'm going to use the full power of this theorem, actually. Okay, and this theorem also, by the way, we'll need to use it. It applies when Alice and Bob have access to public randomness. So basically the theorem, the reduction says that there is a public coin in local reduction, which means that Alice and Bob don't need to communicate to apply it in order to convert a unique disjointness instance in the worst case to a permutation dependence instance of size Q. Again, I don't have time to get into parameters. It's kind of interesting. The parameters here, there's like an opposite dependence on Q, but I don't really have time to get into it. But basically, there is a reduction. And if you plug in the parameters, you get kind of the advantage of streaming that we want. But this is just for one hybrid, Q times S divided by N. So the reduction is from unique disjointness to permutation dependence and then to streaming. Okay, so this was just for first hybrid, right? But we obviously not done because we need to get at the end to the permutation. So let me just sketch to you very briefly how do the rest of the hybrids look like. So the second hybrid gain, we're starting from two independent permutations. So we're going to divide the stream into quarters this time. Okay, so I'm going to say that the next distribution is going to distinguish between either 2 or 4 independent permutations. Okay, so the communication complexity problem will be just a generalized PDEP problem if you want. And again, it satisfies these constraints. But the interesting thing here is that you need to give like you partition the stream into blocks, and you need to give Alice and Bob interleaving blocks in order for them to have the same marginals, right? Because you cannot give just this to Alice, because again, you're Alice could trivially distinguish. So you need to give Alice and Bob interleaving blocks, and this is exactly why the question to answer, this answers Benny's question, why we need actually like this more complicated bounds for disjointness, because now in order to simulate the streaming algorithm, now Alice and Bob kind of need to pass the state backwards and forwards. Okay, so we actually need a more complex, you like to use the full power. And in general, like you can continue this and continue dividing the blocks into halves. At the end, what you get basically is the final distribution. Q elements are divided into Q independent permutations, which is just a random function. Okay, and the maximal advantage, like there is this log Q factor here, which is basically because we are using log Q hybrids. So we get some logarithmic loss. So let me conclude within just 1 minute. So the streaming, what I showed you was basically sketched you as a streaming switching lemma, which is essentially optimal up to polylogarithmic factors. It uses a reduction from communication complexity to streaming, which is somewhat unconventional, okay, because of all these hybrids. And I want to just stress one point before I finish. So why is this? Why do we need all these games with the hybrids? Why does this cannot do this classically? So I just want to say that standard streaming problems are defined in the worst case setting. So in the worst case setting, you can just choose hard instances for the communication complexity problem, and you don't need all these hybrids. However, here, and I think in general in cryptographic settings, the stream distributions are fixed. So you cannot just choose the inputs as you want. And therefore, you kind of need like more sophisticated techniques in order to apply these reductions. OK, so one open question, of course, whether you can use such hybrids to solve more interesting streaming problems. And also, you have in the paper some extensions to multipass streaming algorithms, but that's not extremely important, and that's it. Thank you.
So time for good question. When we turn on the display.
So do you say it at the end? So like Stefan showed for the basic application, there is one square root coming from just, you know, and then you do this PRF switching. So you do naively, you already get square root from the first part. Can you get rid of the first square root, or is it?
No, I got rid. There's no square root here.
You can read from PRF to PRP step.
Oh.
And the original application for encryption.
No, you get rid of the square root. It's not there anymore. Yeah.
No, I mean, so I think you prove it from this, right? I mean, you would need a reference. So I guess it's talking about the reduction from counter mode I gave.
Yeah.
Using divergence, and then you use the switching lemma on that.
Yeah.
So that one is a square root, but you can give a different proof.
Yeah, the proof is different, and you get rid of the square root. It's a completely different proof. It does not use the KL divergence. It's a completely different approach that gets rid of the square root. Yeah.
So essentially, you reduce the problem of distinguishing Q sort of permutation and function on size Q to two problems of distinguishing of size Q over 2 plus the communication complexity cost. So if you just sort of solve this recursively, don't you get what you want? Why do you really need to do this extra?
What do you mean by recursively?
So you, from what I understand, you sort of start with the problem of distinguishing permutation and function on qubits, and then you reduce it to the problem of distinguishing sort of two independent instances.
Yeah.
Right? So this is at most twice the cost of a single instance by a hybrid argument, right? Of size Q over 2.
Yeah.
So don't you get a recursion that says that sort of the advantage for a size Q instance is at most twice the advantage for a size Q over 2 instance plus the communication?
No, I don't see how that would work. I mean, because you get 4. I really don't. I mean, I would happy to discuss this offline, but I don't quite see how that would work. You kind of need to formulate the hybrids, and yeah, I don't see how. Maybe there is a way, but I don't see it. I would formulate this.